This is exercise set 6.2. Since the odd numbered, let me check that. Yeah, odd numbered problems are due for homework. So I'm going to do some of the even numbered problems. Chapter 6 introduces some new rules aside from the elimination and introduction rules. Sorry, my neighbor yelling for her dog. So there's 3 derived inference rules. You can see here I've written them down. Modus tollens, MT, hypothetical syllogism, constructed dilemma. We'll talk about them as they come up in the derivations. There's 1, 2, 3, 4, 5 substitution rules. You'll notice I write the substitution rules and as in the text different, right? The inference rules go from premises to conclusion. If you have this as a premise and this is a premise, you can derive this as a conclusion. Substitution rules, though, are slightly different. As the name implies, you can substitute. If you have something like looks like this, you can substitute something that looks like this, right? The 4 dot symbol here means they're logically equivalent to each other. And you no doubt remember that 2 sentences are logically equivalent, always have the same truth value. So if I substitute this for this, or vice versa, then the truth value will stay the same. We'll talk about some of the main differences between the 2 kinds of rules, inference rules and substitution rules, as we go too. So number 2, all right, P or not Q, one premise, conclusion, not P and Q. So if you look at the new rules, you can see this kind of looks like a De Morgan's, right? So you have disjunction on one side, and you have the negation of a conjunction on the other. So it looks like we might use the De Morgan's rule. Now remember, these substitution rules go 2 ways, meaning if you have something that looks like this, you can substitute something that looks like this, but also the other way around. If you have something that looks like this, you can substitute something that looks like this, right? So these go either way, whereas again, inference rules go only one way, from premises to conclusion. So our first problem, it looks like we have something that kind of looks like this, and our conclusion looks kind of like this. So we'll probably use De Morgan's. But the difference here is, here we have P or not Q. This we have not P or not Q. So we need both of these disjuncts to be negated. Here we only have one disjunct that's negated. But one of our other new substitution rules, the double negation rule, can help us out here. It can change a sentence that's not negated into one that is negated. Right? So P is equivalent to not P. P here, again, remember, stands for any sentence. Right? It could be simple like A or B, or it could be complex like A and B or whatever. So any sentence we can substitute in that same sentence with 2 negations to the left. So that's going to be our first step here. We'll go not P or not Q. We'll justify that by double negation of 1. Now that brings us to another big difference between the substitution rules and the inference rules. Inference rules can only be applied to whole sentences. To do modus tollens, you need a sentence whose main operator is a conditional, and then you need the negation of that consequent to get the negation of the antecedent. If you have a sentence that's not a conditional, whose main operator is not a conditional, then modus tollens is not going to work. In other words, you can't do inference rules on parts of sentences, but you can do substitution rules on parts of sentences. So here, notice that this whole part stayed exactly the same from premise 1 to premise 2. Right? All that changed was this first part. We substituted for P, we substituted not P. And again, that's how substitution rules work. You can substitute in parts or wholes. All right. So here we just needed to do the P because we need, again, to do the De Morgan's, we need a disjunction where both disjuncts are negated. So we've got that now. We can go ahead and do the De Morgan's. Now the way De Morgan's works, one way to think about it at least, is that it factors out a negation. And so this one has 2, so it's going to keep 1. The disjunction turns into a conjunction, and since this one has 1, it loses it, right? So that's De Morgan's of 2. So notice what happened here. We took one negation off of each. In other words, we factored one negation out, to use math terminology. So since this had 2, it keeps 1. The disjunction turned to a conjunction. Since this one had 1, it lost it. It has 0. And you'll notice that's our conclusion, right? I'm using the ampersand for the dot, but otherwise that's our conclusion. So we're done. So before we could do the De Morgan's, we had to do the double negation because De Morgan's requires that each disjunct be a negation. So P wasn't a negation, so we had to do double negation so that it was. Okay, so 2 is done. Let's see, number 4. We've got X or Y conditional Z. We've got not Z, and we want to get not X, right? Now, the first thing that should lead to mind here is if you look at modus tollens again, conditional negation of the consequent gives you negation of the antecedent. So here we have conditional, right? This is the main operator. It's conditional. We have the negation of the consequent. So that means we can derive the negation of the antecedent by modus tollens 1 and 2. Now again, modus tollens has 2 inputs, the conditional and the negation of the consequent. So it's always going to have 2 numbers after it, right? The first number is going to be, or one of the numbers is going to be where I find the conditional, that's line 1. The other one is where I find the negation of the consequent, that's line 2. Alright, now we need to get not X by itself. So again, now if you look at this not X or Y, we have something that looks like this. So we can apply the De Morgan's rule to it, and that'll give us not X and not Y. The substitution rules are always going to have one number because they apply to single sentences. So again, this works kind of the opposite of this De Morgan's. In this one we factored out a negation. Here we're pushing the negation in. So we push the negation in on the X, it gets 1, we change the disjunction to a conjunction, and then we push the negation to the Y, right? So now we have not X and not Y by De Morgan's, and now we can easily get our conclusion, which is not X, and that's by conjunction elimination of 4. All the inference and excuse me, all the introduction and elimination rules are inference rules. All right, so that means they only work one way, and you can only do them on whole sentences, not parts of sentences. Okay, number 6. Conditional conjunction. We want to get not B. All right, so we have not C here, but it's not by itself. So the first thing we can do before we can do modus ponens is we can get not C by conjunction elimination of 2. Now we have conditional negation of the consequence. We can get the negation of the antecedent. And that's modus tollens of 1 and 3. Right, so line 1 is our conditional, line 3 is the negation of the consequent, so that gives us, as a result, the negation of the antecedent. So now we can do we can do De Morgan's, push the negation in, change the conjunction to disjunction, like that. Right, so now we have not A or not B. We need to get not B by itself, right? Now this is not a conjunction, so we can't just do conjunction elimination. And to do disjunction elimination, we need something else. Namely, we need the negation of the other disjuncts. We need the negation of not A. How do we get that? Well, we can get A by a conjunction elimination of 2. Right? Remember, if you have a conjunction, you can get either conjunct by itself. But again, this is not the negation of not A. It's not a negation at all. So to make it a negation, we have to apply the double negation rule. So now we have a disjunction, the negation of one of the disjuncts, and we can get the other disjunct, and that's by disjunction elimination of 5, 7. Right, 5 is line 5 is our disjunction. Line 7 is the negation of one of the disjuncts. As a result, we get the other disjunct. So notice how we're combining the old rules with the new rules. Okay, so this is number 8, and you can see our conclusion here is a biconditional. We have some conditionals as premises and a biconditional as premises. Now, if you remember back to the material equivalence, this tells us a biconditional is equivalent to these two conditionals. So what we can do is we can derive each of these conditionals using conditional introduction and then put them together into a conjunction and use the material equivalence rule. That's one way. Or if you remember back to the biconditional introduction rule, right, it was very similar as far as getting two conditionals and then putting them into the biconditional. So let's try that. So the first conditional we need to get, R want H. So now with R we can get S by 2, so conditional elimination of 2 and 4. We can do R and S by conjunction introduction of 4 and 5. And that allows us to get G and H by biconditional elimination of 1, 6. So remember biconditional elimination here, you have R and S biconditional G and H, you get R and S, so that means that G and H must also be true. Alright, so now we wanted H, remember, so we can get that by itself by conjunction elimination of 7, and that gives us R, then H by 4 through 8. Conditional introduction 4 through 8. So remember, we go back to the original scope line. All this stuff has to be indented and separated from the rest of the proof because it's based on this assumption. Now that's only half of what we need. We need R conditional H, but we also need H conditional R. So we'll do, indent H want R. Alright, should have done this all on one page. So we're going to do basically the same thing. We're going to get G, then we'll do G and H, then we'll use that to get R and S, and then we'll simplify to get R. So we get G by 3, 10, conditional elimination. Then we put them together, G and H by conjunction introduction, 10, 11. Then we use R and S by conditional elimination of 1 and 12. Simplify, conjunction elimination of 13 gives us R. That gives us H conditional R by conditional introduction 10 through 14. And then again we can get that biconditional conclusion. H R biconditional H is our conclusion, and that's by biconditional introduction of 9 and 15. So whenever you have biconditionals, you should think about using the conditional introduction rule twice, because a biconditional, as the rule tells us, is just a conjunction of these two conditionals. So if you can get them both, you get the biconditional. I'm about out of time for 6.2. I'll come back with 6.3.